distinguished guests, ladies and gentlemen, as well as our SUTD family, thank you for joining us on this lovely Friday evening. As a public safety announcement, the emergency exits are situated at both sides of the auditorium, at the center as well as at the back. Should there be an emergency, please make your way calmly to the nearest exit. And now, a very warm welcome to the Singapore University of Technology and Design. I'm Lionel Low, a junior or third-year undergraduate for the Information Systems Technology and Design, or ISTD pillar, and I'm excited to be your MC for today. This year, SUTD celebrated our 10th anniversary as Singapore's 4th public university. We had our celebrations not too long ago, on the 10th of July, which was graced by Education Minister Mr. Ong Ye Kung. We also sealed our very own SUTD time capsule at the campus center that was designed and built by our faculty from the Architecture and Sustainable Design, also known as ASD pillar. You may have seen it on your way to the auditorium. Apart from the two pillars I've just mentioned, there are two more pillars, our engineering product development and engineering systems and design pillars. At SUTD, we are proud to incorporate the art and science of technology and design into a multidisciplinary curriculum that seeks to nurture technically grounded leaders and innovators to serve societal needs. As part of SUTD's ongoing mission to inspire and nurture future leaders and innovators passionate about technology and design, the SUTD Iconic Voices from MIT lecture series is a unique opportunity that features leading faculty from MIT. The series provides a platform for interaction with distinguished experts in the areas of science, architecture, technology, and design. Past speakers include the Edison of Medicine, Professor Robert Langer, President Emerita of MIT, Professor Susan Hockfield, Nobel laureate for physics, Professor Jerome Friedman, and most recently, Professor Susumu Tonegawa, Nobel laureate for physiology or medicine. The Iconic Voices from MIT lecture series is proudly sponsored by Far East Organization. Our speaker for today is Professor Nergis Mavalvala, Associate Department Head of Physics at MIT. Professor Mavalvala is an astrophysicist and a recipient of the MacArthur Genius Award in 2010. In 2016, her team announced the first direct detection of gravitational waves from colliding black holes and neutron stars by the Laser Interferometer Gravitational Wave Observatory, LIGO. Now, the existence of gravitational waves were predicted by Albert Einstein more than 100 years ago, and 3 years ago, Professor Mavalvala and her team were the first to hear those gravitational waves. Professor Mavalvala and her team, wondering how she and her team were able to do that, I'll leave Professor Mavalvala to share her groundbreaking discovery in a bit. The topic for today's lecture is opening a new world into our universe, and the format will comprise a 45-minute lecture followed by a 15-minute question and answer segment. With that, it is now my pleasure to welcome Professor Nergis Mavalvala on stage. Professor, please.
So, hi everybody, you can hear me, I hope. So it's a real pleasure to be here in Singapore. It's my first time in Singapore, and already it is my favorite Asian city. So, so good. Thank you. So today I'm going to tell you the story, and it's really a story of one of the great discoveries of our time. And so without further ado, I'm going to tell you about how we have opened a new window into the universe, and this is going to be the story of the 100-year quest for Einstein's gravitational waves. Now, one thing I have to get out of the way very quickly, right away, is everything I'm going to tell you about, the experiments I'm going to describe, the theory, this is the work of literally hundreds of scientists who are members of the LIGO and Virgo collaboration. So I want to acknowledge my colleagues up front before I go ahead. You can treat me as the messenger for our collective efforts and stories. So if I'm to tell you about opening a new window into the universe, first I must tell you what the old window was. And the old window into the universe tells us about where we live in the universe. So our cosmic address. So we begin right here in Singapore, and you must all know that we are on the Earth. The Earth is part of the solar system. the solar system is actually one of, and our star, the sun, is one of 100 billion stars in the Milky Way galaxy. The Milky Way galaxy itself is surrounded by a supercluster of galaxies called the Virgo cluster. And now, by the time we get out of our solar system to the Milky Way galaxy, we're already talking about tens of thousands of light years in distance. The Virgo supercluster is actually 50 million light years away from us. So now you can see distances are getting big. My point is to tell you the universe is a very big place, all right? And filled with amazing, wondrous things, as you will soon see. Now, as you go further out, we live in a universe that's a cosmic web of dark matter and bright matter and galaxies. And then finally, when we look at the edge of the visible universe, we see this glow of the earliest light, the cosmic microwave background. Now, my question to you is, how do we know all this about the universe? What is the messenger that has brought us this information? And without a doubt, you will tell me it is light. We see light that reflects off of the beautiful buildings of Singapore, light that's emitted by our sun, and light that's emitted by the stars of the galaxy. It is light. That was the old messenger. Now, this old messenger has been a powerful tool for us, and let me share with you one of my favorite pictures in astronomy, and that is this picture here. This is an object called Cassiopeia A, and it is a supernova remnant. So let me tell you what formed this image. It was one of my favorite images because it uses many colors of light. The red and pink colors are infrared light, which our own eyes can't see, but of course snakes could if they could see this object. In fact, and then the green and yellow are visible light that our own eyes can see. And then finally, if you look at the blues and the purples, this is light that's very energetic, right? It's X-ray light. Now, why do I love this image so much? Because it tells us the story of the lifetime of a star, an ordinary star like our own. So what was this object? About 350 years ago, this object was a star like our own star, but like all stars, eventually stars stop shining light because they run out of the nuclear fuel that's burning in their centers. When that happens, the star implodes under its own gravity, and that's what happened to this star. And in fact, at the edges, it sheds out a little bit of material, which we see in the different colors of light. That tells us the energetics of what happened. But I want to draw your attention to the very center of this image. If you squint, especially the people in the back, do you see a small dot at the center of the image, right here? Blue dot. And this is a very important dot because it is the new star that was born with the death of this ordinary star. It is a very special star called a neutron star. And it's only visible, it's only blue, it's only visible with X-ray emission. And it is the star that is formed when this ordinary star collapsed. Now, neutron stars are very extraordinary. They have about the mass of our sun packed into a radius of 10 kilometers. Now, put that into perspective. Our own sun has a radius of 700,000 kilometers. So it's an extremely gravitational object, lots of mass packed into a very small volume. Now, imagine for a moment that this star that imploded and formed the neutron star had been a little bit heavier, the parent star. If it had been maybe 3 or 4 times the mass of our sun, that neutron star would have continued to implode on itself until it became a black hole. So lesson number 1, neutron stars and black holes are cousins. Neutron stars are the lighter cousins of black holes. Now, if it had been a black hole, could we see it? And the answer is mostly no, because it's a black hole. A black hole is an object with so much mass in such a small volume that even light cannot escape its gravitational pull. So the next question we might ask is, if we wanted to observe a black hole, how might we do that? And that brings us to a completely new messenger. Light can't do it for us. Remember, the black hole just eats up the light. And that brings us to gravity's messenger. Now, gravity, as we initially knew it, came to us from Sir Isaac Newton in the 17th century. And most of us as school students or kids who are in school will learn about Newton's universal law of gravitation. And what it basically said was, if you have two objects of mass m1 and m2, they exert a mutually attractive force on each other that's proportional to their masses and inversely proportional to the square of their distances. And this was a very successful theory that explained why planets orbited the sun, why the moon orbits the earth. Apocryphally, it also explained why apples fall to the ground. But Newton himself worried about one question, and that was this question of action at a distance. Newton worried about how does mass 1 know about mass 2? How do they influence each other? And this is something that, in fact, even the ancients like Aristotle worried about. How do objects influence each other without touching, without having some physical contact? Now, this worry of Newton's never got solved until our next hero of gravity entered, and that was, of course, Albert Einstein in the 20th century. And Einstein said something very, very radically different. Einstein said, gravity is not a force. So school students, please sit up. Your teachers have been lying to you. Gravity is not a force, Einstein said. Gravity is geometry. Now, what did Einstein mean by that? Gravity is warpage of space-time. Einstein's picture of gravity is that all of empty space is like a sheet, like you can think of it as a cushion. And if you put a massive object, say like a bowling ball, in the center of that cushion, it will curve. And if you put a playing marble at the edge, that playing marble will just follow the curvature of the cushion and fall into the bowling ball. And that was the attraction. The bowling ball attracts the playing marble because of the curvature of space-time itself. And in fact, Einstein also wrote an equation. Einstein wrote this equation. It doesn't look too much different than Newton's equation, but please take my word for it. It's one of the most beastly equations ever written. And as I tell you my story of the 100 years from the time Einstein wrote these equations in 1916 till the time we could fully solve them and use them, part of it is that these have been very difficult to solve. Now, Einstein also asked another question. He said, well, if you put an object in empty space-time, it will cause the space-time under it to curve, and then you can see that that will cause objects to be attracted to it. What happens if instead of just putting the bowling ball on the cushion, what happens if you actually bounce the bowling ball up and down? What if it's moving, accelerating? In that case, out of Einstein's equation popped a wave. And in fact, it was a wave that is in fact the ripples of the space-time itself. So here is an artistic picture of a grid that would have been completely flat. Then you put a massive object there and it curves because of it. But now you take a massive object and accelerate it, or take two massive objects like two neutron stars orbiting each other, and the space-time starts to ripple, and these ripples emanate outwards as waves. That was Einstein's picture of gravitational waves. Now, Einstein himself didn't like these very much and actually was very ambivalent about them. So he formulated a complete mathematical theory between 1915 and 1918. And then, in 1918, Schwarzschild proposed stars with so much mass that even light can't escape. Now, today we know those to be black holes. Back then, they were called dark stars, and Einstein didn't like these dark stars. Einstein didn't think nature would do such a thing. And he felt the same way about gravitational waves, and he actually vacillated about them, not just about whether they were strong or weak, big, small. He actually really worried, did they even exist? And in fact, in 1936, he wrote a paper with a co-author Rosen, where the title of the paper was, "Do Gravitational Waves Exist?" And if you read very early in the paper, his answer was no. So in 1915 and 16, he does the math that says they should exist, and then he actually says, and by 1936, he says, oh no, they don't. And then he retracted the retraction after discussion. So, he really kind of didn't really feel comfortable with them. Now, the doubts and controversy about these didn't really subside until the late 1950s. But I myself, I'm an experimentalist. I build experiments and instruments, and so I will say this with very emphatic to anyone who will listen, that in the end, none of this mattered, because in the end, only experiment and observation can resolve, was Einstein right or wrong? He had a theory, and until we can prove what nature does, it's just a theory. So what were the experiments and observations that came? So neutron stars, the kind that I showed you a picture of, were first proposed in 1934 by Body and Zwicky. In 1967, Piccini and Gold, two other astrophysicists, proposed that you could have neutron stars that are spinning about their axes. And when they spin about their axes, because they have very strong magnetic fields, their light is emitted like a lighthouse beam. It's a pencil beam that rotates. These were called pulsars. The very same year, in 1967, the first pulsar was observed by Bell and Hewish. Now, in 1969, this man, Joe Weber, announces the first detection of gravitational waves. And this took the world by fire, by storm. He used a device that was, there's his experiment right there. It's a big piece of metal. And the experiment he was performing was that if a gravitational wave passed through this big piece of metal, it would get it ringing, very much like if you clink a wine glass, it rings. And then he instrumented it with sensors to measure that ringing, and that would be a measure of the gravitational waves. Many people quickly joined this effort and tried to build their own detectors. These were called bar detectors, and Weber's claims were found to be false. But he got the world thinking about detection of gravitational waves. In 1971, the first black hole was discovered. And in case you think the first discovery of black holes was extremely secure, it was not. For 20 years after this, there was debate about, is it really a black hole or is it not? So, and this black hole was discovered not, you would say, how would you see one? How it doesn't give off light. These black holes were discovered because this black hole happened to be next to an ordinary star, and it was eating up material from the ordinary star. And as it eats up material, as that material falls onto the black hole, it radiates some light, not inside the black hole, but outside. Okay? That's how it was seen. And then came another very important event, which was these two scientists, Hulse and Taylor, discovered a pulsar in a binary system. And what that means is, I already told you, a pulsar is basically a neutron star, but it's called nature's lighthouse. As it spins about its axis, the beam of light comes across our line of sight. And because this pulsar was in orbit with another neutron star, you could measure that orbit very accurately. Now, I'll give you another important piece of information. Our Earth orbits the sun. Once per year, it comes back to where it was. And every year after that, it does the same thing. Our Earth is not going to crash into the sun anytime soon. Not so for these neutron stars and black holes that orbit each other. As they orbit each other, because of the strong gravity there, they're radiating gravitational waves. Now, gravitational waves are like any other wave. They carry away energy. So where does that energy come from? The energy comes from the orbit, meaning that these objects get closer and closer to each other. Their orbits don't close on each other. They're getting closer and closer and faster until they collide. And this was a prediction that came directly out of Einstein's beastly equations. And Hulse and Taylor make this discovery, and this is a measurement that they made. You see on the horizontal axis is the year. From 1974 onwards, when they first discovered this system, they are measuring the size of the orbit. The vertical axis is simply the size of the orbit. If this system is radiating gravitational waves, the orbit should be getting smaller and smaller. And as they measured over many years, you can see this orbit is getting smaller and smaller. And in fact, the amazing thing about this measurement is that the data are the dots, and the solid line is actually the prediction you would get if you plug the parameters of the system into Einstein's equations. So this was seen as the definitive proof that these systems do radiate gravitational waves. It wasn't a measurement of the gravitational wave itself. It was measured using the light from the lighthouse. But by measuring the size of the orbit, you could tell this was the system was radiating. And this very much impressed Sweden, and they won the Nobel Prize for this discovery in 1993. Now I want to come back a little bit to Einstein. His ambivalence, was it justified? And the answer is yes, because to radiate gravitational waves, this is the only formula I want to put up, but only for people who like such things. I want to point you to two things. To radiate gravitational waves, you need two ingredients. You need the object to be very small. So this is the size of the object, r, compared to its Schwarzschild radius, which is simply the radius of an object of mass m to become a black hole. So you need it to be, the size of the object to be very close to that of a black hole. Our own Earth, if it were to shrink down to small enough volume to become a black hole, it would be of the scale of millimeter. Okay? So even our Earth could do it, but you'd have to compress it down pretty big. So that's the first thing. And the other thing is it has to be relativistic. The velocity of the object has to be close to the speed of light. And if you put those two ingredients together, you can make a very, very powerful gravitational wave. But to do that, ordinary stars don't do that. You need stars that are close to their black hole radii, so neutron stars and black holes, and you need very rapid accelerations. You need relativistic systems. And in Einstein's lifetime, none of those were known. So his ambivalence was really justified. The first evidence for neutron stars and black holes didn't come in his lifetime. He died in 1955, and those things happened in the 1960s. But one of the most remarkable things about Einstein was he didn't like gravitational waves. He didn't think they were right. He wrote this equation that was so hard to solve, but encoded in his math and in his theory were very, very firm and precise predictions for gravity, for spacetime, and for black holes. So now we fast forward to the year 2006, where there were a significant breakthrough using supercomputers in solving Einstein's beastly equations. And so this movie I'm going to show you is actually a movie of an exact solution to Einstein's equation when two black holes orbit each other and collide. So it's quite a pretty movie. Here are the two black holes, and when they're far away, you see the famous black funnels under each black hole, and the two funnels don't really interact with each other, just a funnel here, a funnel there. But because these black holes are giving off gravitational waves, they're going to get closer and closer together, and eventually they're going to collide. And at the bottom here, you see the signal accumulating. This signal is simply the bumps and wiggles of the space-time itself. It's the size of the gravitational wave getting faster and bigger. The movie is going to slow down as these two black holes get very close. And you can see the space-time is really getting very, very warped. Now these two funnels are starting to get very close to each other. And eventually, when the two black hole horizons touch, you will see extremely warped space-time. And eventually, the two black holes will merge and wobble a little bit, become a single black hole. And then the gravitational waves that are emitting will shut off. No more waves, and this black hole will probably sit around dark and in space, never to be observed again. Okay? So and you can see this long list of collaborators who solved the Einstein equations using pretty sophisticated math and supercomputers to ask what would the signal from this black hole look like. Now, it wasn't always so. If we now go back to the 1960s when the first neutron stars were discovered, this man, Kip Thorne, who was professor at Caltech, was among the early people to ask what would the gravitational waves from a pair of neutron stars look like. And this is before these supercomputer solutions that I showed you, and Thorne was among the earliest to show us that the signal would look like this. This is called, by the way, this signal is sometimes called a chirp. And it's called a chirp because it's the exact same sound that birds make. And what you see here is it's a signal that's growing faster in frequency and louder. So it basically starts off, if I were to mimic it with my own voice, it would be whoop. And so it's a chirp of a bird. And Thorne was among the first also to put a scale on it, which was, so this is the gravitational wave amplitude is sometimes called a strain, and I'll tell you in a moment why. It's because it stretches and shrinks space. And he was the first to say, if you take this pair of neutron stars and put it in a galaxy not too far from our own, it will have an amplitude of 10 to the minus 21. And now all the students in the room will be squirming. They must be thinking, what a terrible physicist I am, that I write a number here, but I put no units on it. If you did that on your test, of course, we would dock you points. Now, it turns out that in this particular instance, I'm not to blame. This is a dimensionless number, because this is the amplitude of the gravitational wave is expressed in units of change in length per length. But I'll get to that in a moment. Okay, so that was what Thorne told us. At about the same time, there was also, remember, this is also around the time where Weber had made his claim, so people were thinking about how can we detect gravitational waves. And to go into the detection, I have to say a little bit about what do gravitational waves do here on the Earth. We already saw what they do at the source. So the black holes that are colliding, they give off the waves, and the waves travel through space at the speed of light. And that's what Einstein told us. They're the ripples of space-time itself, and they travel at the speed of light. Now, an important property is that they stretch and compress the space-time itself. And what that means is that as they pass through some region of space, they actually cause that region of space to stretch and compress. So the easiest way to visualize that is to think about what would happen if a gravitational wave went through you, or through me, say. And as this gravitational wave passes through me, I'm a space-time object. What it will do is it will compress me in one direction and stretch me in the other. So if I'm a space-time object like this, notice what will happen. I grow shorter in height, but wider, and back again. That's what the gravitational wave does as it passes through me at the frequency of the wave. Now, and the amount by which it changes the space-time distance is proportional to its amplitude. So that's the amplitude of the wave is h, and it is proportional to the size of the space-time object. So now you can really put some numbers in here. We already know from Thorne's work that the amplitude of the wave should be 10 to the minus 21. Now, take me. I'm a space-time object of about 1 meter. So if this wave were to pass through me, my height would change by 10 to the minus 21 meters. And that's the scale you now want to carry. 10 to the minus 21 meters is 1 million times smaller than a single proton. Okay? And you can see why Einstein was so pessimistic, right? Einstein didn't even know about neutron stars and black holes that have this amplitude. The amplitudes he considered were much, much weaker. But that's the scale of the measurement. Now enters the next hero of our story, this man, Ray Weiss. And Ray Weiss was, this is also in the late 1960s, he was a professor at MIT. And Weiss was thinking about this question of how might we measure gravitational waves, and he came up with the idea of using an interferometer. So how does that work? Well, you start off with a laser. This laser is split along into two parts. One half goes up in this direction and reflects off the mirror up here. The other half of the light goes along this path here on the right and reflects off this mirror here. And the two light paths, when they come back, either the waves will add up and you'll get a lot of light at this output, or the waves will subtract, depending on the path length difference, and you'll get no light. And that was his idea. Now, let me just say something, make a little comment about this. You could, in principle, do a much simpler measurement. You could, in principle, do a measurement where, imagine that I have a laser, which happens I do, and imagine that at the end over there is a mirror. I could shine this laser at this mirror. The light would reflect back, and if I had a good clock, I would measure the light travel time. And then, as a gravitational wave passes through, that light travel time will change because it changed the space-time distance. And so the principle of the measurement is as simple as that. It turns out just we don't have clocks that are good enough. And as a result, you have to make a measurement like this where you can think of one arm acting as a reference for the other arm. And that allows you to make the measurement without having an absolutely precise clock. Now, this idea came to Weiss, and it also came to a couple of others around the same time. But the thing that Weiss did that was very important was Weiss understood very quickly that you couldn't make a device like this that's only 1 meter long. Because remember, then the change in distance, remember me, the change in my distance was going to be 10 to the minus 21. So Weiss proposed that we should make interferometers that are 4 kilometers or 4,000 meters long, and then you would have to make measurements of changes in distance of 10 to the minus 18 meters. And that's only 1,000 times smaller than a single proton, and he said to us in 1972, we can do this, and he showed us how to do it. He has one of the most famous papers never published. So the whole concept for the experiment that he proposed was published in a paper, was written up in a paper that was never published. Okay? I don't recommend this for academics in this moment in time, but then it worked. So Weiss and Thorne met in 1975 and conceived of the experiment, a 4-kilometer long experiment called LIGO, which stands for the Laser Interferometer Gravitational Wave Observatory. And you can see from these aerial pictures, there's the cartoon I showed you earlier, and now you can see from these aerial pictures, these are 4-kilometer long L-shaped versions of that cartoon. And now I'm going to tell you a little bit about how the measurement is made, because you must be wondering, aren't these people crazy? How in the world can they make a measurement of 10 to the minus 18 meters of motion of the mirrors of these interferometer? So I'm going to tell you about 2 factors of a trillion. The first factor of a trillion is, what is the measurement we're making? We're making a measurement that says if a gravitational wave comes by, the mirrors will move, and we should measure that. By how much does the gravitational wave move the mirrors? By 10 to the minus 18 meters. If I just plop a mirror down in this room, it will move by about 10 to the minus 6 meters. So that's your first factor of a trillion. You have to isolate the mirror from all the forces on the Earth by a factor of a trillion. And we do that with vibration isolation systems that look like this. This is an active system, and we hang the mirrors as pendulums. And between all of those technologies, we can make a mirror that's still at the level of 10 to the minus 18 meters. Then comes the next factor of a trillion. Suppose I've done that. I've done that really well. The mirror is really still. How can I measure such a small motion? Now, ordinarily, if I asked you to measure the length of a piece of paper, you would say, fine, I'll give you a ruler, you can do it. If I wanted you to measure, say, the thickness of the piece of paper, you would have to get a little bit more clever. You might have to use a vernier caliper or something like that. How in the world are you going to get down to measuring 10 to the minus 18 meters? So there enters the L in LIGO, and that's the laser. So we use the wavelength of the laser light as the tick marks on our ruler, okay? And so now comes the next question. We happen to use light that's very close to visible. It's actually near infrared, and the wavelength of our laser is 10 to the minus 6 meters. But we need to measure 10 to the minus 18 meters. So the tick marks on our rulers are 1 trillion times bigger than the precision of the measurement we want to make. Now what do we do? And so the way we get around that is we use very powerful lasers that allow us to average over many, 10 to the 22 photons per second. And by doing this averaging, we can resolve the measurement at 10 to the minus 18 meters. And we do that by using a big laser. And in fact, inside this interferometer, then nearly 1 megawatt of laser light has to propagate. So those are the 2 technologies. Now you should never forget, you have 2 factors of 1 trillion that's needed. I've swept many things under the rug, but that's the basic idea. Vibration isolation and then precision optical measurement. Okay? This effort in the United States was funded by the National Science Foundation over 3 or 4 decades. And then this man, Barry Barish, is the person who is credited with taking these ideas of Weiss and Thorne and helping to turn them into facilities, large-scale facilities. And you'll see these characters will return. Now, LIGO is not the only game in town. There's a global network of detectors. There's the 2 LIGO detectors in the US, one in Washington State in a desert, and another one in Louisiana in the southeast in a pine forest. These are 4 kilometers long. The next longest detector is the Virgo detector in Italy, and it's a French-Italian collaboration. It's a 3-kilometer long detector. That's also operational. And then under construction is a 3-kilometer long detector in Japan called Kagra. And then there's a plan for a future detector in India. And there's also been for a long time a proposed plan for a gravitational wave detector in space called LISA. So now we fast forward. LIGO has been built and is starting its second phase of operations. And on the 14th day of the 9th month of the year 2015, the first binary black hole collision is detected by LIGO. And so here is what happened. 2 black holes collide exactly as Einstein instructed them to. The gravitational waves from these radiate outwards. They travel across the universe, and in some cases quite a great distance. And eventually, remarkably, they cross our beautiful planet. So here's the gravitational wave. It hit the Louisiana detector first. 7 milliseconds later, it hit the Washington detector. Please note the Earth did not wobble like that. Remember, in the end, it was only 10 to the minus 18 meters, right? But you get the idea. The wave came through, travels at the speed of light, so it came to the Louisiana Observatory first, and then to Hanford. And this is what the signal looked like. This is now an iconic figure, but I'll tell you a little bit about what it means. So on the horizontal axis is time. On the vertical axis is strain. Remember, strain is just change in length per length, or the amplitude of the gravitational wave. And these are the data from the 2 detectors, and they were actually 7 milliseconds apart, so one data stream has been shifted by 7 milliseconds, so they lie on top of each other. And you see something remarkable. The first thing you see is here are the actual ripples of space-time itself. These bumps and wiggles are the bumps and wiggles of space-time. When these 2 objects, which turned out to be black holes, and I'll show you in a moment how we know, when the 2 black holes collided, the amplitude of the gravitational wave was 10 to the minus 21. It's an enormous check mark for Kip Thorne. He told us that in 1967. The amount by which the LIGO mirrors moved when this gravitational wave went through was a few times 10 to the minus 18 meters. It's an enormous check mark for Ray Weiss. He taught us how to do this in 1972. Okay? Now, what does this signal actually tell us? So here is the theoretical model for that same signal. It's just a little cleaner to see. So what we see is that from the fact that the frequency of the signal is changing, the change in frequency depends on the mass. So from that, we can tell what the mass of the 2 objects was. Once you know that, then from the amplitude of the wave, you can tell how far it was. And then finally, from this last part of the signal, which is from the frequency and the decay time, you can tell what the mass and spin of the final object, of the new black hole was. So from the frequency evolution, you can tell the masses of the 2 parent black holes. From the amplitude, you can tell the distance. And then from this last bit, the ring down, you can tell what the new object formed was. And now we can take this and piece together the story of the 2 black holes. So once upon a time, 1.3 billion years ago, there existed 2 black holes. They did a dance around each other, and because they're radiating gravitational waves, they're going to get closer together and collide. This is a beautiful simulation. It's again an exact solution of the Einstein equations, but this time these black holes have been put in a star field so you can see how the starlight is bent by the black holes as well. And these simulations were developed initially by Kip Thorne's group for the movie Interstellar. Okay? So Kip Thorne is a man of many talents, and he also works in movies. Now, what we could tell from this final black hole that was formed, here are now the properties that we could tell. The 2 parent black holes were about 30 times the mass of our sun. Now here you really have to hold on to your seats. I'm going to tell you something that's really blow your minds away. These two 30 solar mass black holes, when they collided, that moment of collision, they were moving at half the speed of light. Imagine that. These objects were about 250 kilometers in size, 30 times the mass of our sun, moving at nearly the speed of light. Very relativistic system. They were 1.3 billion light years away. Thank goodness. We wouldn't want to be much closer. Well, a little bit closer would have been convenient, but not anywhere in the actual vicinity. And then the other thing that we learned is that the newly formed black hole, this newly formed one, was 3 times the mass of our sun lighter than the two parents. So 3 times the mass of our sun was radiated away in gravitational waves in those 200 milliseconds. And this is seen as the most powerful explosion ever observed since the Big Bang. Okay? So that was the story of those black holes. As you see, they did not live happily ever after. But I want to make a slightly philosophical comment. Even though those two black holes didn't live happily ever after, they gave up their lives to give birth to this new black hole, very much like human parents on the earth do, right? So the story of life continues even in the universe. Okay. Since then, we've seen many other black hole collisions. In fact, we have seen a total of 10 black hole collisions with combined observations of LIGO and Virgo. And I'm not going to go through the details of those, other than to say that by measuring more of these systems, we are starting to answer some questions about black holes. The questions we'd like to know is, how are they born? How do they form? How do they live? How do they die? And so those are the kinds of questions that we're able to answer from this collection of black holes. So we see Einstein's theory seems to be correct. It was the first to predict the existence of black holes, and they behave the way that he predicted. Gravitational waves seem to behave the way that his theory of general relativity would say. They travel at the speed of light. We're able to measure that. They have the expected geometry. Black holes exist and they even form pairs. Until these observations, that was not a guaranteed fact. We didn't know. We expected, but we didn't know. So that's seen. But now one of the beauties of scientific discovery is that as soon as you learn something, you also immediately know you don't understand the system very well at all. You also have new puzzles to solve. And the question is, how does nature make such heavy black holes? We actually don't know how 30 solar mass black holes form. We also don't know how they form pairs. Do they form pairs because they were born as twins already in a binary system? Do they form pairs because they're isolated black holes that meet each other and capture each other due to their gravity? We don't know, and those are the kinds of questions that we can answer as we measure more and more of these black hole systems. So black holes were pretty exciting, and we were very happy with that, but then something else very spectacular happened, and this was on August 17, 2017, when LIGO and Virgo detected the first collision of neutron stars. Now, neutron stars, even though they're the lighter cousins of black holes, they have one very important difference. Neutron stars are made of neutrons. And when neutrons collide, you get a spectacular light show. This is the collision of, basically, it's a collision of atomic nuclei. Remember, neutrons are the building blocks of atomic nuclei. So when LIGO and Virgo observed this first merger of neutron stars, we were able to alert 70 telescopes worldwide to go look for this expected light show that should be there. So what happened? So here was the detection of the signal in LIGO and Virgo, and this is a way of representing the chirp. It's the time versus the frequency, and you can see its frequency is getting faster, and that's the chirp. And we knew right away that it was a neutron star and not a black hole, because the black holes all had lasted for about a few seconds at most, under a second, a few hundred milliseconds to a second. This signal we were able to measure that lasted over a minute. And that means it's lighter. Now, shortly after LIGO and Virgo saw the merger, 1.7 seconds later, a gamma ray telescope saw a signal, a very loud signal. And we expect that. We expect that as the neutron stars collide and these neutrons are bashed into each other, we should see the gammas. So the gamma rays came out. Now, it turns out that because of the way that gravitational wave detectors, the 3 gravitational wave detectors work, we could localize that this source was in a patch of sky, about 30 square degree patch of sky in the southern hemisphere. Now, at the time that we made the measurement and the 1.7 seconds later that the Gamma Ray Telescope, which is a space telescope, made the measurement, it was daytime in the southern hemisphere. Bummer. There's a big old sun out there, can't see very much. But the good news was that astronomers then had something like 11 hours to prepare for this observation. Now, for astronomers looking through telescopes, when you tell them that to look for something in a 30 square degree patch of sky, that's pretty difficult because telescopes have a very small field of view. So they have to actually raster through a big patch of sky to look. But the telescopes prepared for this, and then what followed was what I would call a sort of an astronomer's night to remember. And so a bunch of telescopes looked, and this is a very busy plot, but I want you to only carry away a few things. What you can see is gamma ray, gravitational waves, gamma rays, X-rays, ultraviolet, optical, infrared, radio. Every color of light that we looked in, we saw something. What's the something that we saw? So I'll draw your attention to these. These are all names of different telescopes. And on the bottom left of each of these squares is the time lapse since the LIGO Virgo trigger. And so notice that this is a galaxy. It's NGC 4993. And you see this crosshair where you see a little bright object? Now look at this. Oh, missed it. Yeah, look at this. This is the same telescope looking at the same galaxy 20 days earlier. Look in the crosshairs, there's nothing there. That object lit up that night. Okay? And so by measuring its properties, we've learned a few things, but let me next show you what do we see. So this is an artist's movie of what would have happened. Here are 2 black holes orbiting each other and only giving off gravitational waves. There's no light being given off at this point. And then when they collide, see these jets? Those are the gamma rays. And then after that comes all the different colors of light that are given off by the nuclei fusing into atomic elements. So I'll show you one more time without talking at you. Notice. Neutron stars and gravitational waves only. When they collide, the first thing is the jets of the gammas, and then other light. Can I make this go again? Maybe. Okay, there you go. Music is thanks to NASA. They always do very dramatic things, so that's nice too. So what we then see is you can go out and look at the time that's elapsing, and each of these is different colors of light. And at different times after the collision, different colors of light become dominant in this neutron star remnant, we know. And each of these peaks corresponds to an element of the periodic table. So in this movie of these different peaks as days go by, I am showing you the fusion of elements. Okay, and this is going to be very important because it solves an important mystery that we've had for a long time. So this single observation of a neutron star colliding due to that we see first in gravitational waves, because we see it in gravitational waves, we can ask telescopes to look at in the right direction, has taught us some very important new things. So the first thing we learn is that neutron star mergers are the cause of the gamma ray bursts. We've had a mystery for almost 30 years. We've seen gamma ray bursts of a certain kind, these particular short kind, that we've seen in telescopes, and we've not known what they are. And we've suspected that they should be due to the mergers of neutron stars. We've never captured that in real time, and that was done. The next thing we've done is actually something really amazing. So here we are, we've observed this neutron star collision, 140 million light years away, and it has taught us something about the Earth and about ourselves. So let me tell you what that is. For a long time, we've had a mystery here on the Earth. We have too much gold and platinum and heavy elements. What does it mean, too much? Too much because we don't know where it comes from. Most of the elements that we are made of here on the Earth come from stars like our own sun. But stars only fuse elements up to about iron, which has a mass number of 56. Heavier elements than that, the sun doesn't have the energy or the neutron source to do that. So the next thing you would think of is that maybe they're formed in the explosions of stars, so supernovae. And when you look at how supernovae operate, you also can't you don't get the abundance you need of the heavy elements like gold and platinum. So for a long time, decades, we have imagined, hoped, suspected that these heavy elements are fused in neutron star collisions. And now, for the first time, because of those different colors of light I showed you, we have confirmation. If you look at this periodic table, everything that's yellow are elements that are formed in neutron stars, as measured by this one neutron star we saw. In fact, we saw many tens of Earth masses of gold being formed. Okay? So here is a mystery. So, astronomers and especially used to famously say, we are all stardust, because we thought all the elements come from the stars. Now we have to modify that a little bit. We are all neutron stardust. Yeah. And then, most remarkably, it also says to us that sometime before the formation of our solar system, here in this vicinity, there must have been a neutron star collision. So it tells us about our history as well. Now, the third thing we learned from this single neutron star collision was we were able to independently, using gravitational waves, measure something called the Hubble constant. Now, the Hubble constant is a number that mostly only astronomers love, but I'll tell you why you should care too. The Hubble constant is a number that we measure out in the universe that determines the history and the future of our universe. So we should like to know what it is. It tells us what rate our universe is expanding at, and will it continue to expand, will it slow down, will it speed up. So it's an important number, and it's been measured using light. Remember, until now, light was our astronomical friend. And by using light and using different methods with light, we get different answers, and we don't know what the right answer is. And so we now have an independent measure of that using gravitational waves, which are different than light. And believe it or not, the answer using gravitational wave lies between the two answers with light. But with enough uncertainty that we need more measurements to get it better, to get a better handle on it. Okay, so these are some of the things that we've been able to do with gravitational waves. So I want to tell you that we think we're opening a new window into the universe. We think we're launching an era of astrophysics. And here are the things we know so far. We have had these first direct observations of gravitational waves. We know now that Einstein's theory of general relativity, this part of it has been confirmed. We see that these binary black holes, pairs of black holes and pairs of neutron stars, we've seen these collisions in real time, and we're learning about the building blocks of our universe from that. And I must say, for myself personally, as an experimentalist who has spent my entire career building the LIGO instruments, it's really great that the goddamn instrument works too, with the precision that was needed, okay? And that's a really nice thing too. So never forget. Thank you. Yeah. So never forget, if you build a good instrument, you will learn something, okay? And so these are the things that we celebrate today. But I think I want to put this into perspective. I think this is much bigger than this list of things that we've achieved over the last couple of decades. Really what we've done is we've turned on a completely new way to look at the universe. We no longer rely only on light. Now we can look at the gravity of objects, and that can be a tool for really discoveries of the kind we haven't imagined as yet, okay? And so going forward, I want to leave you with a slightly philosophical way of thinking about this. Oh, let me just say, so a slightly philosophical way of thinking about this, which is that we believe Galileo was the first person to point a telescope at the sky in 1609. Okay, so it's been a little over 400 years since then. And Galileo's telescope was a small little 1.5-inch refractor. Most toy store telescopes are almost as good now, because of technology advances. And no one really remembers what Galileo saw. He saw craters on the moon. We can see them so much better now. He saw the phases of Venus. He saw the rings of Saturn. That's not what we remember Galileo for. What we remember Galileo for is the paradigm shift. Galileo was the first to tell humans, you don't have to use just your naked eye to look at the sky. If you use an instrument, you can do a little better. And if you make your instruments better, you can do a lot better. And if you look at that, since the time of Galileo, in the 400 years since then, we've built a 100-inch telescope in the early 20th century. We've put a 100-inch telescope in space. That's the Hubble Space Telescope. We're now building 25 and 30-meter class telescopes. In the meantime, we've also built telescopes that look at other wavelengths of light, infrared, gamma ray, X-ray, radio waves. And that's how we have pieced together the picture of the universe I showed you at the very beginning. And I want to leave you with this thought that the gravitational wave sky and gravitational waves are very much the same. Like light, gravitational waves span 20 orders of magnitude in wavelength. And every different wavelength of gravitational waves brings us information about different objects in the sky. We've only touched the tip of this iceberg, but by looking at these very fastest gravitational waves. These are these objects that are moving at tens to hundreds of times per second around each other, neutron stars and black holes. But there's this whole range of objects that radiate at different wavelengths, and including one of the most amazing of all the possibilities with gravitational waves, which is the ability to look back all the way to the Big Bang. Now, I have shown you very early on in my talk, I showed you the cosmic microwave background, the very first light that we got from the universe. It turns out that this very first light that we see, it was actually emitted when the universe was 400,000 years old. Still a short time in the lifetime of the universe. The universe is about 13.5 billion years old. But the reason is that light was trapped inside the hot, dense universe because photons are very interactive. They like to zip around and they interact with the matter. The way that you can think about this, the way I like to think about this, and hopefully it will help you, is it's a little bit like if you're in a crowded room, say you're at a party, and you want to leave. And if you want to leave with your friend who is an extrovert, then your friend it'll take you an hour to get out of the room, because every time you meet someone, you have to sit and you chat, and eventually you get out. Photons are like that. When the universe was young and dense, photons kept banging into electrons and protons, and they just couldn't get out. Gravitational waves, on the other hand, are completely aloof. They're like going to the party with the introvert. You say, let's leave, and you're lucky if they'll say thank you to the host. They're out the door. And so the gravitational waves have been streaming to us from the early universe, from the very beginning. So when we look at if we want to look farther back in time to the beginnings of the universe, that's our messenger. So I hope I leave you with this idea that we've done remarkable things. We've made this measurement that was very precise. We've learned about black holes and neutron stars, and we'll continue to. But really, this is the beginning of something much bigger than this moment in time. So thank you.
Wow. Thank you, Professor Mavalvala, for giving us an exclusive look into the new window of the universe. May I invite you to take a seat on the center of the stage, please? I'm sure following that session, many in the audience will have intriguing questions to ask Professor Mavalvala. The next segment will be the question and answer segment. Members of the audience are invited to ask any questions they may have. For that, joining us on stage as a moderator is SUTD's president, Professor Chong Tao Chong. Let's put our hands together to welcome Professor Chong on stage. We'll now be opening questions to the floor. If you have a question, kindly approach the microphone along the two aisles. Please also introduce yourself with your name, as well as the organization that you're from before asking your question. In the spirit of fairness, we'll be alternating the questions around between the mics in the room. So without further ado, can we first have the gentleman on the left?
Yeah, please, Charles. Yes, as you mentioned, I'm Charles from SUTD, final year student at SUTD. I have two questions. One is, could you elaborate a little about LISA, the space LIGO, and also, since you plotted the gravitational waves like a wavelength, in the same way you might plot light, do you think gravitational waves can be quantized like photons?
Very good. So, is this on? I guess this is on. Good. So, yeah, let's start with LISA. So LISA has a concept quite similar to LIGO. LISA is a configuration of 3 spacecraft that fly in a triangular formation, and each spacecraft has a laser on board that it shines to the next spacecraft. And so in the case of LISA, and each spacecraft also has a good clock. So in the case of LISA, the light leaves one spacecraft, arrives at the other, and it's clocked there. And so that's the measurement procedure of LISA. LISA is very complementary to LIGO and Virgo because it measures at wavelengths that are much longer or shorter periods. And so lower frequencies, rather, I should say. So on the Earth, we are unlikely to be able to measure gravitational waves with frequencies of lower than a few hertz, just because the Earth is very vibrational and very noisy. And so if you want to measure lower frequency waves, you have to get off the planet. And there's good reason to want to, because, for example, supermassive black holes, which we know are at the centers of galaxies, these are black holes that are 1 million to 1 billion times the mass of our sun. Those are emitting gravitational waves not at 100 times per second, but much more like once every few hours. And so that's the wave frequencies at which LISA would detect. Your second question, can we quantize gravity? So the answer is people have been trying for a long time to do that. These measurements, I don't think will have much bearing on that process, at least not now at the sensitivities we have. And you need much more precise measurements to say anything about quantized gravity. That said, you can ask the question, if gravity were quantized and if its particle were a graviton, which are all ifs, then we can actually put a limit on the mass of the graviton from the measurements already. But it's not a very meaningful thing to do because we have no theory to compare it to. Okay?
Okay, all right.
All right, thank you.
Yeah, maybe I just want to follow up on that question here. You mentioned that in order to observe higher frequency gravitational wave, you had to get out of the planet.
Lower.
So is it possible to build LIGO in space?
Yeah, so for lower frequencies, you have to get off the planet. Building an interferometer in space is very, very difficult because you have to maintain the spacing between the arms of each arm too precisely. LISA gets away from that, so the LISA spacecraft can drift relative to each other. But because you have, and the LISA's path length is 5 million kilometers. So you don't need as much precision, right? Because your change in length then that you're trying to measure for the same size gravitational wave is 10 to the minus 12, not 10 to the minus 18. So building an interferometer would be much harder. There are conceptual proposals out there, but it's pretty hard. And in fact, there are some Japanese groups that are working pretty hard on it. So it's not crazy, just hard.
Or we see it the other way around. Is it possible to create the kind of black hole pair collision on Earth so that we don't have to wait for 1.3 billion years to happen?
That's right. So first of all, we don't wait 1.3 billion years. It's because even though that black hole collision happened 1.3 billion years ago, they're happening all around us. In fact, I showed you 10 that we've already measured. And now, with advanced LIGO and Virgo have had some improvements in their detectors, and we're now detecting at roughly one event per week.
Okay.
So, these as they get better, you see more events because, of course, the universe is big. Building a source of gravitational waves here on the Earth is it's really impossible to do. And I'm not someone who says impossible lightly. So you can do a very simple-minded exercise where you can say, well, you can take a dumbbell, and you can put the dumbbell on a rotation state. So you spin a dumbbell, and then you can make some crazy numbers. Say the masses on either side of the dumbbell is 1 ton, and you spin it up to a few hundred hertz, which is the sensitivity where we have our sensitivity, and you put it as close as you can get. And even then, the numbers will work out to something like a gravitational wave amplitude of 10 to the minus 33. Okay?
Yeah.
And that's already laughable. We don't even know how to do that. So we have to rely for these systems on astronomical objects. And even though they're at a great distance, they have enough mass.
Okay, thank you. 10 to the minus 31.
Yeah, something crazy.
We will never graduate.
Oh, that's right.
Okay, next one, please. Oh, sorry, this side, yeah.
Dear Professor, thanks for your talk. So I'm interested in the goal, too much goal on Earth. So what happens after the 2 neutron stars collide? Like for the black holes, we saw they became a black hole. And the 2 neutron stars, they collide. And after that, do we see that?
Yeah, it's a very good question. So in this observation, we don't know. Most likely what happened, based on the masses of the 2 neutron stars, is that once they collide, they became heavy enough to just become a black hole. So the remnant is probably a black hole. Now, the light that we see is not from the black hole. It's from, in the collision, some of the material gets blown off. And that's the part that's giving off the light. As you saw from that movie, it's an object called a kilonova. It's basically a material that is already reacting. So the center in there, somewhere in that cloud, there must have been formed, most likely, a black hole. The only other alternative is a heavier neutron star. But neutron stars, just from neutron buoyancy, they can't be much heavier than 2.5 or 3 solar masses. So if it's heavier than that, it had to just collapse to a black hole.
Thank you.
Okay, good. Now, your turn.
Good evening, Professor. I'm Li Shuo, a student. So I got 2 questions to ask you. Number 1 is, you mentioned that the 2 black holes of 30 solar masses, when they collided, they lost 3 solar mass for some reason. So I was wondering, since black hole cannot, no information escapes the black hole, how does 3 solar masses suddenly disappear off the black hole?
Yeah, so remember, that's not quite right. Information is not lost from the black hole. Information, in this case, the gravitational waves are coming to us, and that is information. And that information is coming from the orbit of the black hole. Nothing can escape from inside the horizon. But there's plenty of dynamics that are happening outside the black hole that you can still have. So that the information is coming from the dynamics of the black holes outside of their black shroud.
Oh.
Okay.
So the second question is, how do the gravitational waves transmit or lose energy?
Yeah, so that's another good question. So the amplitude of the wave falls off as 1 over distance. So so the further you get from the object, the amplitude of the wave is falling off. And that's just what you expect as the wave spreads out, in a spherical shell. The amount of energy that it actually deposits, you can ask the question, how much energy did it deposit in the LIGO mirrors as it went by? And that's the part that's really tiny. That's why it translates to such a small motion. So the energy transfer is not very efficient at all. And in fact, that's the same reason. The reason is that the gravitational waves don't interact with matter very much, right? So the energy deposit is very small.
Okay, thank you.
Yeah.
Okay, good. Yeah. Question here?
Yeah, hi. Just asking about concerning that 2017 detection. Which information do you use to deduce which part of the sky it came from?
Okay, so that's again a very good question. So it turns out that gravitational waves are a little bit like our ears as opposed to our eyes. We perceive sound through triangulation. And gravitational wave detectors work the same way. They're not like telescopes. They can't pinpoint at a source. The way that we tell where the source is by triangulating the waves that come from the source. And so that's part of why it's so important to have many gravitational wave detectors, because the more you have spread out over a larger baseline, the more precisely you can tell where the source is.
Okay, good. Please.
Hi, good evening, Dr. Mavalvala.
Really?
I really enjoyed your lecture.
Thank
I
you.
should say that I'm a bit starstruck at the moment. My question for you is not specifically regarding LIGO, but it's about the progress of physics and the future of physics in general. In terms of theoretical physics, from the point of view of an outsider at least, it seems in terms of new paradigm shifting ideas that progress has been slowing since perhaps developments in quantum mechanics several decades ago, in terms of new paradigm shifting ideas. And as theory becomes more and more complicated, experiment needs to be bigger, more expensive. And surely LIGO has achieved a great deal, very remarkable progress, and has opened up a lot of questions for future research. But there's a question of whether the short-term economic incentives are strong enough to fund new research, and whether that is sustainable in the long run. So my question for you is, regarding these challenges in physics, do you think these are real causes for concern in general? And also, do you think that, or rather, what areas of physics in general, so slightly unrelated, but what areas of physics in general do you think show promise for new paradigm shifting ideas in this sense? Thank you very much.
Yeah. So look, that's a really tough question to answer. So I'll try. Look, in terms of the environment in which we're doing science today, and sort of the short-sightedness and short-term returns that experimental endeavors have to give, it's a problem. Ray Weiss, who is my PhD advisor and who I talk to regularly, will tell you very clearly that he doesn't think something like LIGO would ever get off the ground in today's environment, because it was too risky, too long-term, and with unknown outcome. Personally, I think the way to address that, and this is true for funding agencies, is also true for people building their careers, students. You should always choose some fraction. You choose the number, whether it's 25%, 20%, 30%. You should always do some fraction should be moonshots. Things that are really hard, but if they pay off, it'll be really good. And then the rest of your portfolio can be more safe, and therefore also a little bit more boring. But so that's how I would address that that question. In terms of paradigm shift, look, I think the only ways that you get paradigm shifts is when you do open-ended, curiosity-driven research, because you don't set out to change paradigms, right? And so I think that's another important thing. Applications are very important, but again, some part of your portfolio should be sort of more fundamental.
Perhaps we should think like Einstein. Yeah.
Oh yeah, completely outside the box.
Okay. Now, Nergis, I think we are overshot the time. Are you okay to
I am totally
answer a few
fine.
more questions?
Yes, gladly. And I see
Now,
finally the women
so,
are out, so I would love
but we
to
also
hear the
know that
questions.
people have to leave here, so maybe we should not add to the list anymore. I mean, waiting list. So I think we have 5 here. Maybe I ask this side to ask the first question, and then the second question you answer both at the same time.
Okay, we can
Okay.
try.
Yeah, this one first. Yeah.
Hello, Professor. My question is quite theoretical, and it's with regards to the general unified theory. I know that black holes are the region where both quantum mechanics and general relativity interact. So could the discovery of gravitational waves, the detection of gravitational waves, since they are with relation to black holes and neutron stars, could they somehow aid the making of a general unified theory?
You know, I'll answer that question because the answer is quick. In principle, yes. With the precision that we have right now, no. So in the future, remember, we're looking at this long view, 400 years after Galileo. So in time, yes, but not at the present precision.
Okay, please. Yeah.
Thank you.
Hello, my name is Cadence. I want to ask if it's possible for 3 black holes to collide into each other.
Absolutely, yes, it is possible for 3 black holes to collide, but it usually doesn't happen. Normally what happens is that the way this works is usually for 2 black holes to start orbiting each other, you almost always need a 3rd black hole, but usually that poor 3rd black hole gets kicked out of the system. So usually you start with 3, and then 2 will form the pair, and the 1 will get kicked out. And that's just because of the way momentum has to work. So, but it's a very good question.
Okay, yep, please.
Okay, cost 285. You see, in a nuclear, when you have more protons, you need a lot of neutrons to stabilize this mass. With such a dense black hole metals, how do you get all these things squeezed together? Does the proton lose the charges so that they become neutrons and combine together so that they can be dense together?
Yeah, so I think the composition of the neutron star is largely neutrons, and it's supported by a neutron degeneracy pressure.
Yeah.
And I actually don't know off the top of my head what fraction is protons. There are protons in there, but I don't know.
Very
what
much less.
Yeah, much less. Yeah.
Okay.
And just one question.
Last question.
Because the Earth is not uniform, you know. So in a desert, the temperature changes a lot. So how do you compensate the distance difference of your orthogonal axis? Do you float the axis on so that you...
Yeah, so you know, things that change on the time scale of days or night-day cycles, those are all very easy for us to handle because we can compensate for those. The measurement we're making is at 100 hertz, and those changes are happening on the hours time scale.
Okay, thank you.
So, yeah.
Okay, good. Yeah.
Hi, thank you for your talk. I just want to find out, because your...
I thought the queue should stop there. Still kicking up. Yeah. Okay, go ahead, yeah.
Because the gravitational wave is changing space-time, right? So doesn't the wavelength of your laser or even time itself...
Yeah, look, that's a very famous question that gets asked, and it was hotly debated in the early days. So the question is, if the space-time is stretching, then doesn't just the wavelength of the light stretch, and in the end, the light can't measure anything? The answer is no, because we don't care about the wavelength of the light. Remember, I told you the measurement itself, I pointed my laser there and said the measurement, we measure light travel time. And light travel time is independent of the wavelength of the light.
Or even the time that there's no time dilation because of the...
It's independent.
Oh,
yeah.
okay.
Okay, good. All right, this side left with 1. Good. Yeah.
When we work in the lab, usually we never get exact theoretical curves for stuff in general. But it's the same for LIGO. You didn't exactly get the...
Absolutely. Yeah.
But in like, for example, classical mechanics, you always have friction and other stuff which attenuate the signals and stuff. So in this case, I don't see exactly where, like, why exactly it's a little different from what you would expect theoretically.
Yeah, so the reason the curve isn't exactly like the theoretical curve is that in all experiments, including ours, there is noise and uncertainty in the experimental apparatus itself. And that's why it deviates. And in the theory, there can also be uncertainty, but in the experiment, it's random. And the randomness is the thing that makes our measured bumps and wiggles not exactly the same as the theoretical ones. Okay?
Do you think there could be like gravitational wave interferometry at some point?
No, so gravitational waves don't interfere. Just the same way as light waves don't interfere if light just passes through each other. These are completely incoherent sources. And when you have incoherent sources of waves, they don't interfere at those, at those scales. So no, that's not the effect. It's really just, it's very explainable by noise in the instrument.
Okay, good. Yeah.
Thank you.
Okay, so thanks so much for your talk.
You're welcome.
And so you mentioned that energy is sort of deposited at the LIGO detectors.
Mhm.
So does that mean if gravitational waves pass through enough objects, they get absorbed and like you wouldn't be able to see them anymore?
Yes, eventually, but their interaction is so weak that we think they'll pass through to the other side of the universe before that would happen.
Oh, okay.
So-
And sorry, I've got one more. So is there like a reason we have so many LIGO detectors being built around the world, apart from just to confirm the readings?
Yes, so the reason is primarily the one I said a couple minutes ago, which is to pinpoint where a source is on the sky, you need multiple detectors because that's done by triangulating. And so, and not only do you need multiple detectors, you'd like them to be as far apart from each other as possible so that you can resolve the signals.
Okay, thank you.
You're very welcome.
Okay, thank you. All right. Last question. Yeah.
Hello. So I'm going to ask a question about science in general. So I think cosmology and the scientific institution in general has become one of the most powerful ways to understand our place in the universe and what our place would be in the future, right? And from our current vantage point, we can see that a Hubble constant will result in several million years from now, galaxies disappearing from our view. So a civilization being born further down the line wouldn't be able to observe what we have been able to observe through our artifacts such as light or even gravitational waves. So what are our limits of empirical science in general and the horizons of our knowledge? Thank you so much.
Yeah, so look, I think those two things are not necessarily related. So what you say is certainly true. The universe is expanding, and its expansion is accelerating. So eventually there will come a time when all stars and galaxies have moved so far away apart from each other that you're left in darkness with no neighbors nearby, right? So that's the thing. And that's and you know, we think that's where we're headed. We're not certain yet because we need to know more. And that is, I would say that's on the time scale not of millions, but really many, many billions of years. So, you know, the universe is 13.5 billion years old now, and we see that. So I'm not.
What is to say that it hasn't already happened? Something similar in terms of scale?
I could have. See, look, one of the things we don't know, and we can speculate and dream, but we don't know is we don't know what the universe was before the Big Bang. Did it exist before? Was it a universe that expanded and then bounced back? So, you know, there's this idea of the Big Bang and the Big Crunch and then the Big Bang. So there's a cyclic way that universe expands, collapses, expands. We don't know the answers to those things. But to me personally, that's the whole reason we do science.
All right, that's awesome. Thank you.
Okay, thank you. Now, I think as a moderator, I can ask the last two questions, okay?
Of course.
Well, I think you study about space, so I'd like to know whether you have thought of going to space.
Do I personally think of going to space? I think as a kid, you know, I certainly might have dreamed about it. But as an adult, to be honest, no. I don't see. I personally don't see. Other than the achievement of it, as a scientist, there are not necessarily strong reasons to put humans in space.
Okay.
So.
Now, my last question has to do with SUTD.
Excellent.
Okay. So, in SUTD, we are quite successful in getting female students to the university. In fact, we have about 40% girls in our undergraduate. So, as a female physicist, scientist, and you are in a field that dominated by male, I think so. So can you maybe advise some of our female students here how you overcome this you know, maybe the situation you face, or maybe encourage them more?
Yeah, so look, I'll say a few things about that, because I get asked about that quite often. So first of all, I say mainly to the women, but of course this is true for all young people who are building their careers. You know, find your allies and mentors. They are there. No matter how often you're told you're not good enough to do this or you shouldn't do this, there are people out there who believe you should and can. So find those people, and those are your allies. So find your allies and mentors. The second thing I'll say is, The world is changing. It is getting better, slowly, and sometimes you take steps back and then you go forward again. But it's changing, so stick with it. If it's something you love to do, stick with it, and also be tough. If someone tells you you're not worthy, punch them. But metaphorically,
Prove them wrong.
Yeah, that's right, exactly.
Okay, thank
so
you.
Yeah, I have many of those things.
Yeah.
So it's been a real pleasure being here, so thank you.
So let's thank Professor Mavalvala.
Unfortunately, all good things must come to an end, and that's all the time we have for today. Thank you everyone for your enthusiasm and participation, and thank you panelists for your time, insights, and inspiration. On behalf of our SUTD family, may I invite Professor Chong to present a token of appreciation to Professor Mavalvala. We have now come to the end of the iconic Voices from MIT lecture. Let's give another round of applause to our guest speaker for today, Professor Mavalvala. Once again, thank you everyone for your time at SUTD. We would also like to take this opportunity to invite you to our next event, which is the Capstone Exhibition on the 7th of August. The exhibition will showcase 68 innovations by our graduating class of students, which are essentially their final year projects that aim to solve real-life problems, most of which are commissioned by companies. With that, I'd like to wish everyone a great evening and weekend, and we look forward to seeing you again. Thank you.